all halo properties. So I need to focus on a few things that is probably, I thought were, first I knew more about them, and second they are more pertinent to the subject of this workshop and to this kind of things that people have been thinking about. And I'll focus on questions of galaxy halo connection. What is a halo? How we define a halo? What is a halo mass? And also we'll try to touch on assembly bias that the people after me will be talking about. Now, the reason we talk about galaxy halo connection to death, to such lengths, is because we don't understand it. And the reason, one of the big reasons we don't understand is because we don't have ability to directly model, reliably directly model formation of galaxies inside the dark matter cosmic web that is collapsing from initial Gaussian conditions. So a picture like this, where you see dark matter distribution in grayscale, we understand pretty well. We think we can simulate it from first principles and understand the physics involved and the properties of halos that form. But how baryons dissipate, form stars, and how the stars affect their surroundings remains poorly understood. And so, although there is very strong evidence, I'll show that there is a very good connection between galaxies and halos, what this connection is in detail, so the accuracy that we need to get unbiased constraints from biased tracers is still something that needs to be understood and work in progress. I'll just give you one example of a completely randomly selected paper that's appeared on arXiv a few weeks ago, but this is very representative. So representative of the state of galaxy formation that we're in. So this I'm talking about direct modeling of galaxy formation, not semianalytic, not abundance matching, not age matching. I attempt to actually follow the collapse of baryons, conversion to stars, and how those baryons react in the environment. You see baryon fraction, so this is mass of baryon in the galaxy divided by its halo mass, and I'll come back to the definition of this halo mass in a little bit, and divided by universal fraction of baryon. So ideally, when halo would collapse, and if it was able to collect all the baryons available to it, a sort of universal share of baryons, and then convert them into stars, this number would be unity. The actual galaxies, the galaxies in the real universe, are shown by points here. There's now a number of constraints which have some scatter, but nevertheless, we have some idea about what real galaxies are doing. And as you can see, what they're doing is that they're converting about a quarter to a third of the potentially available baryons into stars, and even at mass of about 10 to 12. And that seems to be the maximum. The larger galaxies have convert less, smaller galaxies convert also less, and these trends, suppression of star formation, continue to both higher mass and lower mass galaxies. The gray bands here also are reflecting what we think real galaxies are doing, but they are obtained not with a direct observational constraint, but through simply empirical modeling, using a method that's kind of broadly can be characterized as abundance matching in different redshifts. So the lighter bands are higher redshifts. This dark band is redshift 0. One of the remarkable things about the galaxies is that this type of plot doesn't seem to evolve with redshift very much. So that galaxies at different redshifts have of the same mass have converted roughly the same fraction of universal baryon fraction into stars. That's one of the puzzles that actually needs to be understood. What I wanted to draw your attention to are these color lines, the dashed line, the blue line, the purple line, that correspond to a simulation of a galaxy in the same here is a key word, 10 to the 12 solar mass halo. So we're starting from the same initial conditions, and all we're changing is some parameters of how stars, of implementation of how stars are converted into, how gas is converted into stars, and how stars are doing the feedback on surrounding gas. And you can see that the lines turn out to be quite different in those three cases, even though all of the simulations are following the same dark matter distribution. And maybe this difference doesn't look a lot to you, but this is log scale, so it's factors of several. And visually, if you look at these galaxies that end up in each of these halos, in one case, when the feedback is weak, we end up with a very dense and very spheroid-dominated galaxy. In this middle case, where a galaxy ends up in stellar fractions somewhere among observed galaxies, we end up with a late-type nice disk, late-type galaxy with a thin disk with maybe some small bulge. And in this case, we end up, again, with the same halo, we end up in a galaxy that looks very disturbed, very irregular, and very extended. So the point is that in the same halo, we can form galaxies of 3 different morphologies, right? And the one that looks most like observations of galaxies in this halo mass is this one, but really, what I should want to draw attention is this variation, right? And we don't quite understand the physics that goes on. So which one, I mean, we understand that this one probably is incorrect, this one is incorrect, but we don't know exact physics that we should be putting in reliably to predict galaxy properties, right? The feedback, what we do understand is that the feedback is absolutely crucial. So to form a galaxy like this, the stellar feedback has to be incredibly efficient. I won't show this movie, but in order to have this suppression, the galaxy has to undergo sort of repeated blowouts at high redshifts, very dramatic blowouts of gas in interstellar medium. For higher mass galaxies, the edge-in feedback also leads to repeated dramatic blowouts. And the feedback, because it originates on sub-parsec scales where stars form or AGN operates, but then creates winds that are global out to megaparsec scale, it couples scales. It couples small scale to large scales. And this is very difficult because if all the feedback effects we can concentrate on small scales and information will just flow in one way, we can just ignore it. But because it couples scales out to megaparsec, we cannot ignore it in all situations. So as many of you know, when we look at weak lensing, cosmic shear power spectrum, the effects of feedback can propagate all the way to L of 200 in terms of angular multiple, and so on. And the effects are not very strong, and we don't know exactly what they are, but this is like a representation of different hydro simulations. Most of them are quite crazy. So this scatter is probably pessimistic compared to what really uncertainty should be for more realistic models. But nevertheless, it gives you an idea that different implementation of hydro processes that lead associated with galaxy formation will lead to different power spectrum. And this is, we're not talking about 1% here. You can see that variations of 10%. And this is something that could be a challenge to model, although people have been very clever in coming up ways to characterize this without full knowledge of what baryonic process should be. And there's just a sampling of papers over the last several years which attempted to essentially model away these effects, but with Newtons, with relatively few Newtons parameters. And it looks like it is possible. What this forms the basis for actually talking about halos and talking about halo models and talking about modeling halo bias and then using it to model galaxy clustering is the fact that despite all this strong feedback property operation, in the end of the day, the galaxies do exhibit very tight relation between stellar mass and halo mass that you can see here. This is something that people have theoretically expected and sort of relied on because all the models of galaxy clustering for the last 30 years relied on the fact, it's an assumption, that galaxies form in halos. And there is one-to-one mapping between them that we still maybe not understand. It's complicated, but there is mapping that can be modeled. This is actually observational evidence that such mapping exists between stellar mass and halo mass. The points here, again, this is actually replotting on the same plot that I showed before, but now just directly, not through fraction, but through stellar mass and halo mass. And different points are weak lensing, satellite kinematics measurements. One is by actually people in this room contributed to producing these points. Our contribution in this paper was to the cluster scale, where we measured stellar masses of central galaxies and clusters and masses through X-rays. And you can see that galaxies form this nice sequence, which is nonlinear and is offset from this universal baryon share. So this is effect we think is effective feedback. But nevertheless, there is this tight relation, right? Which gives it more or less consistent from different methods, at least at this scale. There are still questions about scatter about this relation. We have some idea what the scatter is. For example, for clusters, because we're dealing with individual systems, we can just measure it, and it's about 0.17, 0.2 dex around the mean relation. There are constraints from some of the studies, for example, from satellite kinematics, which was done by Surhood et al. And Frank. There's also, as part of this analysis, they obtained constraint on the scatter, and it's also about 0.16, 0.2 dex. But we don't know how the scatter behaves with mass, for example, how it changes with mass. We don't have a good idea. Also, recently, there are repeated, actually not recently, but over the years, there are repeated indications that the red galaxies and blue galaxies have relations that are offset from each other in the sense that red galaxies of given stellar mass live in more massive halos. So that's a complication that also has to be kept in mind, potentially, and needs to be explored. But nevertheless, this is a basis. So galaxy maps to halo mass, and therefore we can work with halos and try to understand what real galaxies are doing. What I wanted to do is to actually examine, there's a lot of things on this side, how we get this quantity and how it depends on, how this relation depends on color. But I want to go even more basic and talk about the halo mass. So when I put plot like this, I put something like M200, but what is M200 and why did I put M200 there, right? So the question of what is halo mass is really, yeah. So the differences, I believe, it must deviate at some level, but I think the differences right now are within this scatter that you see between.
If you go to low mass.
Oh, at low mass, maybe, right. But all the surveys so far have focused. So at low mass, I think this relation may well break down or become much more complicated. The surveys so far have focused on galaxies mostly in this regime, although in some cases people are getting very close to 10 to the 9, but mostly in this regime, right? But in small mass, I agree. It can completely break down. You don't agree? Breaks.
Basically, there are no red galaxies.
Yeah, that's very few, yes.
What you're talking about is mainly a satellite.
There are a few red galaxies there, but they were just recently quenched, like in the last enriched 0.3. So they would be, just having gone off of that curve anyway. So at low mass, the risk is the same.
Yeah. But overall, I would expect, personally, my gut feeling is that this relation will actually become the scatter should blow out. It's just physically, because these galaxies are more susceptible to effects of feedback. But we don't know directly. It's just a sort of prejudice that I have. So to talk about halo mass, what is a halo mass, how it's defined, is really to talk about what is a halo, because we can't define halo mass without defining what halo is. And I think in everybody's mind, the definition is clear. It's kind of implicit that the standard thinking is that halo is a peak in nonlinear density field. Of course, we heard yesterday a lot about Gaussian, peaks in Gaussian field. But when we talk about halos, we're talking about nonlinear fields. But still, we're talking about peaks, right? Because when a halo finder goes into simulation and tries to find halos, it looks for peaks in the density field. And the peaks it identifies have overdensity, density contrast of thousands or 10,000, depending on the resolution of the simulation. So it's something much, much larger than amplitude of typical Gaussian field at the starting initial condition for structure formation. So it's a halo, it's a peak in nonlinear evolved density field. And usually people think that it's something that's defined by a certain density contrast. And all the operational algorithms used to define halos in simulations in practice are essentially implementations with different assumptions of this generic definition. And the main ones that I use is friends of friends, so-called friends of friends, that's been used for a long time, both for simulations, this paper, and for clustering, identifying groups and clusters in observations. This was Anasta. That's the first paper I know that used it for cosmology. And it defines halo to be a connected region bounded by isodensity surface. So a surface that corresponds to a given density contrast. And the nice thing about it, it's not spherical. The bad thing about it is that if you look in detail, this definition has a lot of problems because, for example, the overall overdensity that you end up with for the halo is strongly resolution dependent. It's also strongly mass dependent, strongly redshift dependent. So you can only be certain that it identifies halos for a given density contrast for a fixed redshift, for a fixed cosmology, and for a fixed mass. If you change any of those things, the overdensity actually changes. And so interpretation of that in terms of this definition actually becomes very tricky. Plus, it's easy to show that, for example, things like cluster observables correlate poorly with this mass. So there's quite a few negatives. Nevertheless, it's theoretically very attractive to many people because it can be implemented in a very simple, mathematically pleasing algorithm. The less pleasing definition, but I think which was practically more useful, is spherical overdensity. This one is extremely like a spherical cow picture of the halo, where halo is defined as a region around a density peak that encloses a given density contrast. And then you define the mass using this density contrast, which is defined relative to some reference density. And the choices for reference density, sometimes people use critical, sometimes people use mean. In principle, it doesn't matter because you can always refactor this. They're only different by factor of omega matter, and so you can always refactor it in delta and cast it either as a critical. But it does matter when you talk about an evolution of the property, because critical density and mean density evolve differently. They depend on redshift differently. But this is the second definition, which is also quite simple. And you can ask, well, does it matter how you define the halo? And if you look at the literature, majority of studies seem to operate on the assumption that largely it doesn't matter. You can just define halo mass. There is also a third question that arose yesterday, which is, what is the connection between the mass that people define for halos in extended projector theory, right? Which is a mass that you get within some filter, which you apply on a linear Gaussian density field, and the mass that people measure in simulations. That question, I think, is almost never addressed directly. And there's some belief that there's somehow the two are connected and you can match simulation on the Gaussian peaks. But I think as we get to better and better accuracy, this question pops its head very, very often. because that connection to me doesn't look trivial and very easy to understand. So that, I think, were the question where we also have to pay attention to how we define halo mass and which halo mass actually connects the best to the mass that people use in extended projector models or any other analytical models of bias and galaxy clustering. Right. What I think is the most salient thing about this, to think about these definitions, is that the density contrast values. So okay, you can define halo within a given density contrast, but the values that I use for density contrast are very poorly motivated. The best motivation we have is that there is this delta that is used is result of some spherical top hat collapse model. But real halos, if you've ever seen a movie or studied how halos actually form, they don't form by spherical top hat collapse because initial Gaussian peaks are not top hats. You may approximate them by top hats. And the difference between a Gaussian peak and a top hat is that top hat collapses at the same time. So you can define a very nice formation time, very well-defined formation time. At that time, you can define the density contrast at which halo virializes. But even that process is actually wishy-washy because virialization is usually swept under the rug. So the number that comes out from a spherical top hat collapse model relies on a very strong simplifications, the approximation of Gaussian peaks by top hats, and completely ignoring what happens during visualization, the fact that visualization in real halos takes a non-negligible fraction of a Hubble time. Right? You can see this arbitrariness in the fact that people use different definitions in different papers. And a lot of people ignore exact dependence of what you expect from top hat collapse, for example, as a function of cosmology, and just use 200 over density of 200 for definition of mass. Some other people actually take it seriously and use the virial over density, so-called, the number that comes out from top hat collapse, predicted at different redshifts for different cosmologies. And you can find all of these choices in the literature. And the fact that there are these choices and different people use different things is itself reflection of the fact that motivation is quite arbitrary. If there was a strong motivation that everybody more or less would use the same thing, right? You can also see that this motivation is weak if you look at the density of halo. So this is a density profile, so relative to mean density of the universe, as a function of radius defined to virial radius. In this case, virial radius. Once I've heard James Bullock say, I'll define virial radius as the virial radius. So in this case, it's a virial radius is defined using the precise prediction of top hat collapse model. So not 200, not fixed, it's actually changing with it. But for this purpose, it doesn't matter. And so halos of about 10 to the 12 solar mass selected for this plot. So they're more or less the same mass, and they're stacked. So there's many halos, and you can see the scatter. So the halos have this very well-defined profile. You can see the slope of this profile as a function of radius. And then here, there are different choices that people often use in the literature to define the edge of the halo. You can see that the choices vary by quite a bit, so the difference between them is substantial. But you can also see that there's nothing in the profile at those radii that really would tell you, okay, there is a boundary, physical boundary of the halo there. You can see here that the slope really doesn't care about any of those radii, so it just keeps going. If there is any characteristic radius, is this one, right, where suddenly slope changes and you can see it as a flattening. The closest radius to that is R200 mean, but it doesn't match it exactly, right? And this radius where this transition happens is larger than any radii that people typically use, okay? You can say, well, again, what does it matter? I can define any of this radius, even if there is arbitrariness. There are many examples where you can show that it does matter. One example I'll show you is halo concentration. So this is, the concentration of halo is something people care about because it's often used in models of halo formation and galaxy clustering and so on. So here is the concentration. Concentration is defined as a ratio of radii, so radius that you use for defining your halo, and the radius where, so-called scale radius, where the logarithmic slope of the density profile is about -2. And of course, if you have different choices for delta, you'll end up with different concentrations. So what you see here is concentration defined with respect to radius of using contrast of 200 relative to critical density. This is this virial definition, and here is 200 with respect to mean density. And again, so mean density and critical evolve very differently with ratios, so you end up with rather different definitions. They are plotted as a function of corresponding peak height. And what you can see is that behavior as a function of redshift, different colors are different redshifts, and behavior is very different. If you care about universality of halo concentration, so for example, the fact that you stack them by peak height and you end up with the same function in different cosmologies and different redshifts, you see that for none of these cases, it's universal, but it's most universal for this quantity. So if you're trying to build a universal model for concentration, you may argue that this is the best definition because it actually reduces the scatter. Well, in general, yes. So we don't expect it to be universal. But if you want to build universal, it's best like you have one parameter and you want to reduce the variance as much as possible. And if you cannot reduce it to 0 with mass definition, for example, you can't reduce it to 0, then you search for the second parameter, right? That's exactly what we did here because you look at different definitions and the best you find is for this one. And then you still have some variation with redshift, but it's much smaller, factor of 2 or more smaller than say for 200 mean. That's right. Right. But there is a preceding literature, there's a number of papers where people actually claim that it's universal and new. And so here in our paper, we show that no, it's not universal. And you guys also showed it. And this is the next one. So there is a second parameter. So we talked about second parameters beyond mass yesterday. The second parameter here is something related to properties of Gaussian peaks. We actually didn't find a statistical property of a Gaussian peak that would give us a Gaussian field that would give us the second parameter, but we clearly see that concentration, this is in this definition that I think would be best for universality, it does depend on the slope of the Powell spectrum. And that's something that was pointed out before in Zhao et al. As well. These simulations you see here, simulations of cell-similar models. So omega is 1, the spectrum has a power law slope, so there is really, you can you expect everything to be universal on those models as things evolve. And different pieces of lines here are actually different redshifts. So you can see that in a given model, everything lines up along this line, but the amplitude does depend on n. You can calibrate it using these simulations. You can say, okay, I know that it depends on the properties of the Powell spectrum, and the local slope, for example, can parameterize it and actually fold it back into this initial non-universality. And here you can see that this evolution with redshift, you can parameterize with dependence on slope because a given fixed nu at different redshifts correspond to different slope of the Powell spectrum. Right, because halos and peaks collapse from a somewhat different part of the Powell spectrum, which has somewhat different slope. So if you fold this dependence in, you can actually explain this evolution and then predict this behavior into other cosmologies fairly well. And this is something we showed in this paper. If you're interested, there is a code that you can use which implements this parameterization. But this is not the relevant point here. The relevant point is that definitions of halo mass and halo boundaries can matter, right? So it's worth considering them more carefully. I didn't talk about this part of the plot, so I focused only on Milky Way size halos before, but look at the cluster size halos, right? So this is the same stack, but now for halos of about 10 to the 15 solar masses. You can see that the shape of the density profile visually is quite different. Yes. So observational measurements of concentration proved to be quite difficult, but they've improved tremendously in the last 3 years or so. And I don't think they inform us yet about what is the best definition. At least that's my take. But there used to be a disagreement between prediction of simulations and say measurements of concentrations in groups and classes, and that disagreement went away as people understood how to treat errors and propagate errors of the analysis better. So right now, if prediction of this concentration model is compared to Clash survey, it looks like a fit to the data, even though it's not a fit, it just goes through. So there is perfect agreement. But I don't think data informs us about choices not yet. Yeah, and actually, so
that's why we use isolated halos.
Well, that also, but this was also one of the reasons that I'm not going to talk about. But
for the concentration studies, we always use isolated halos. Galaxies don't have close pairs, so there's no. It's all a profile. This thing that he's seeing on large R, that's the two halos.
Yeah, that's right. And the difficult part in the modeling. Yeah, but you still project the same. If you have a problem in modeling 3D distribution, you will that problem will project also in 2D, right? To some extent, right? And actually, so because there is this very strong transition, so people traditionally over the last 20 years focused on modeling this part, which was highly important because that's where galaxies live, right? But the outer regions of the halos where really interesting things happen, and you start seeing deviations from the, say, anisotropy or NFW profiles that are designed to fit the inner part. This part was relatively neglected, and that's where halo models usually had some problems in matching the mass distribution. So how to transition from to large scales where we can model things, from small scales where we can have approximation from simulations. I think the way to go is actually to have a holistic view and try to model the entire thing to calibrate in simulation. That's a view.
I think that one thing here is that whatever you do, right, if you do consistent, that's fine. But I think one motivation that we want to talk somewhere is that within that region, as the plot is showing that, within that region we have universality. The scale is small, so that we can really do, if we calibrate whatever or got something, then we can apply everywhere. As soon as you go to some places, the fluctuation is so big, then basically you cannot really say much, right?
Right, except that
one of the motivations.
yeah. Except that if you look in detail, so outer regions have their own scaling. They scale, for example, well with the radius defined with respect to mean density, but that scaling is different from inner regions. So if you care about the outer regions, you may apply actually again different scaling, use different radius to. Yeah. No, I said it was neglect theoretically, relatively. So, and it's not just neglect, it's just that you focus on the most important things. So people have been focusing on inner regions of halos. But I think outer regions become highly important because that's where we can actually see, observe now through recleansing. And that's where models, traditional models, because this transition was not, modeled, modeling was not focusing on it. Usually that's where the errors were largest. Transition from one halo. It's a transition region from one halo to two halos. I don't know. So where one begins, ends, and one begins depends actually how you define your halo, right? So for some people, this already would be two halo term. For some people,
have a joint paper from 10 years ago.
yes.
All fit your simulations perfectly, right?
Well, at what level? I mean, the simulations were 88 inverse megaparsec. So at the level of 10%, you can get away with lots of things. So we're talking about going to the era where accuracy required is higher than that. Yes, if your accuracy was on the level of 10 years ago, 88 inverse megaparsec simulation, if I came out here and actually showed you clustering results from 88 inverse megaparsec simulation now, people would laugh at me, right? At that time, it was state of the art. So things are different now. And we have to be paying attention to small errors, more subtle effect. And the fact that I want to point out is actually not that subtle. It's kind of surprising why it was missed or why people didn't look at it. But you can clearly see, maybe because, in order to see it, at redshift 0, where people mostly look, you have to look at a load of 10 to the 15 solar mass halos. So you can see that the different profiles are different. Mostly it's difference in concentration, but there is an interesting thing here near the virial radius, where instead of just going flat, like you see for galaxy profiles, suddenly profile steepens to all the way to -4. And again, this is a stack, right? So this average behavior. There are some halos actually even steeper. There are some shallow, but on average they go very steep. So that's slope that's not predicted neither by NFW nor by anisotropy. It's very, very steep. And then suddenly it goes back to large-scale structure, to two-halo term, right? So this is a feature, right? So if you have a feature which is quite sharp in the profile, it means that you have some sort of physical edge, right? And maybe you can squint and so you say, I don't see this very steepening, but this is average. If you look at an individual halo in detail, this is a density profile in a slice through a cluster size halo. You can see this edge easily, right? Most of you see it, right? Right? So the halo is embedded in cosmic web, but there is this clear edge, and this is not stretch of this image. You can actually, if you look at detail for density gradients through these regions, you can see a sharp drop. The origin of these edges is very clear theoretically. So again, you could say that they were expected, and the reason I don't know why they weren't seen in simulations before, but the expectation for this type of edge comes from the earliest models, some of the earliest models of halo collapse, so which went beyond the top hat and modeled collapse of matter onto a peak in successive sort of successive stages, right? So there's still some, the first models use still spherical symmetry. Later models used ellipsoidal distribution, and they more or less predict the same result, that you build up a profile which is close to isothermal. Exact slope does depend on the slope of the initial peak that is collapsing and so on. But one feature that is actually common to all of those models is the fact that the profile undergoes a drop before it goes into large-scale density environment. And this drop is physically corresponds to so-called last caustic. I used to call it last caustic. We use it now splashback, and the person to thank for this is Neil. So if you have problems with this name, blame him. So this is a phase diagram. This is radial velocity as a function of radius and units of turnaround radius. And you can see material unfolding, going through the center, turning around, and going to the upper center of its orbit, where it moves slowly and kind of piles up. And this is successive shells. So material accretes at different times and then kind of wraps around and starts orbiting. This is what we call the virialized region of the halo. This one is the last accreted material that just had enough time to complete an orbit and reach this upper center. But you can see that in this case, it's very clear what is the physical edge of the halo, right? The region that separates the material that orbited at least once from the material that just unfolds for the first time is this radius. And if you project it on density, because you're projecting multiple streams, you actually end up with a drop, right? So physically, we understand where it comes from. The situation in real halos is very messy. So this is an example movie of from demand and cooling, where you see the same phase bias diagram, but now with all the merging, with all the massive hierarchical structure formation. But in the end, at redshift 0, where things quiet down somewhat, you can see a similar pattern, right? You see infall, you see turnaround, you see this wrapping around, and then you see this splashback radius. What I want to point your attention, this is actually 10 to the 12 solar mass halo. I want you to pay attention to two things. One is that even at redshift 0, this 10 to the 12 solar mass halo does accrete material. Although if you look at it in the density profile, it looks very static, right? So from the profile, you may think that the thing barely accretes. But in the phase diagram, you can clearly see that there's material with negative velocity that comes in. The second is that the splashback is also very clear, but look at where it is. It's 600 kiloparsecs, right? So it's way, way larger than the standard virial radii that we're using, which would be in this range for this halo, right? Twice larger. It's almost. Yes, it can pump back and forth, yeah. So, but still, at all low redshifts, it's around 500, 600 kiloparsecs. That's almost a distance to Andromeda. So if Milky Way had such large splashback, its inference region, where we could expect, for example, satellites to be affected, would be much larger than the virial radius that we typically use. So if you care about modeling red galaxies or assembly bias, you must care about this, because it shows you that the region of inference of a particular halo could be much, much larger than you would think if you use the virial radius. Okay. Yeah. Actually, no, because so that's another puzzling feature which was fooling me for a while. If you look at this line, this is a median velocity of particles vertically, and you can see that it's not flat. So it's actually positive here. So when you average this positive velocity, so outer regions of the halo have positive, even the material that already orbited has positive velocity relative to the center. And that's actually very generic. You see it in this halo, but you can also see it in other galaxy-sized halos of this kind. So if you average this positive velocity material with this negative velocity material, you can get something close to 0. So if you look at there, it should be negative, yes. But there it depends on right. It depends on how much material you have here, so how negative you'll be. But yeah, right. Now the reason the splashback can be so large is actually because its radius depends on accretion rate. So this is actually something generic. So this is comparing the edge of the halo that you saw before to other definitions. So this is the virial radius. This is 200 critical. This is the typical ratio. If I take just generic peak height of one halo, this is the typical ratio between those radii that I find. But different halos have different ratios between splashback and, say, 200 mean or critical density. And the reason for this is that this position of the splashback depends on mass accretion rate. So this is one illustration from a paper we did with Surhout this year, which illustrates this. So there's two different cluster size halos, and you're looking at the density slice through the halo within something larger than splashback radius. And I don't know if you guys visually can tell which one is a strongly accreting halo and which one is a slower accreting halo here. No? Even you can tell? Yeah. So when you have slow accretion, essentially what happens is that majority of mass is already settled, and then the slow late accretion, when it's slow, essentially creates this very diffuse extended halo. Whereas when accretion is slow, everything kind of is boring, everything is concentrated, everything came in more or less at the same time, well, or relatively small delta t, and so things are more or less distributed in the same radius. So this is a fast accreting halo, this is a slow accreting halo. And when we predict average splashback radius from the average relation for halos of this mass, or for halos of that accretion rate, we more or less get something that's close to where we actually see this edge. And you can see that relative to R200 mean, so say dot dash line and the splashback dash here, they well separate. But here they're almost identical, right? So the relative ratio for these two halos is different. And you can actually characterize this if you measure for each halo the mass accretion rate and split halos of the same mass but different accretion rates. So this is again the second parameter. You see that the position of the splashback, the strengths, and also the strengths of infall, so this is the difference of accretion rate, are different in these different halos. You also see a related difference as a function of peak height. So if you look at halos at a given redshift at different peak height or mass, so peak height here defined in the usual way, you also see that the splashback is different for different halos. But again, this is a related effect because there is a difference on average in the mass accretion rate for halos of a different peak. So clusters today accrete more, galaxies accrete less, and so you have this sequence. But the primary variable that drives this dependence is accretion rate. And we can show this by just taking one nu, splitting by accretion rate, and essentially generating a trend like this. That's what you saw in the previous plot. Right. You can ask, mostly what I showed you was clusters. Can you see this for galaxy halos? The answer is yes. I won't go into detail. But here you see similar density slices through galaxies with our attempts to identify this surface, which in some cases are difficult, but overall is quite successful. So there'll be a paper on trying to do this for individual halos on galaxy scale soon. And in some cases, very clear. So this is a 10 to the 12 solar mass halo, and you can see the very clear splashback, just like around clusters. Some halos like this are in much more messy environment where things is more difficult. You still see splashback surface here, but the picture is complicated by the fact that this halo is embedded in the filament, and filament has its own caustic, its own splashback. And so you have multiple sharp density features. This fact that galaxies, different galaxies that mass see different environments, you can actually see in the density profile. So you see a lot of scatter here and very little on clusters. We typically think about clusters as being very messy and not scaling very well. But actually clusters scale well because they are the biggest kids on the block. So they dominate the environment. So once you stack on their profile, the outer regions, they more or less shape them. So they're more or less the same and reflect the potential well here. While galaxies of a given mass can live in a variety of environments. And that's what you see in this large scatter here, right? That's
so the slope change that you have, the sharp comes before the splashback radius.
it starts before in this average profile. In 3D, when we look at 3D density field, it's usually very sharp, but because the surface is not exactly spherical, it has some shape, which actually is interesting to explore. What is the shape and how it varies with mass? When you spherically average it, it extends. It starts to be, it starts at one radius and then kind of continues, and so it has some non-negligible delta R associated with it. So this difference in environments gives rise to the effect called assembly bias that already was discussed yesterday. And the point I want to make is that it's very strong effect because you can see it visually. This is a paper from one of the first, this is a figure from one of the first papers that talked about this, Gauto, where they split the entire halo sample that you see here. So this is just a slice through a box for millennium simulation into earliest and latest forming 10%. And you can clearly see that the two samples of halos having the same mass cluster visually very differently. And this is a fairly large effect if you measure the bias. The point I want to make is that this assembly bias is, you can see it as a function of different properties of halos, not just formation redshift that you can see here, but also concentration, which is some people think is a different way to define formation ratio, but it is a different way, but they define to something different because the effect you see is also quite different. You see effect both on small scales and large scales, large masses, whereas for this definition on large masses, there's barely anything. We'll hear a talk by Sir Hood that about the fact that at large masses there seem to be assembly bias. So this means that the property on which he uses to split observation is more related to this property. There's also dependence on spin parameter, for example, and probably some other property of halo. Essentially, clustering of halos depends on many different properties of halos, and how it depends on the property. So you'll get different results for different properties. That's actually one of the most worrying things about our ability to model galaxy clustering with the halo picture. Something even more worrying that started to rear its head. This paper was from this week, which was pointed out that not only there's assembly bias, but actually there's also scale dependence, at least out at about 5 megaparsecs in their case. There's some signature, and maybe we may hear more about it from Urosh, I don't know, that the scale dependence of assembly bias, there's a scale dependence even to larger scale, but that's something that we're still exploring. It's something that was seen in the figure in our paper, but it's something that we're trying to figure out right now. So to summarize, what I wanted to show you is that direct simulations of galaxy formation are making huge progress. They definitely show that the feedback is crucially important, but the feedback byproduct is coupling between parsec scales and megaparsec scales, and that's something that makes modeling of mass distribution and galaxy clustering on small scales is quite uncertain, and something we have to live with in modeling it as a nuisance parameters. The traditional halo mass definitions are, I try to argue, that quite arbitrary. This is maybe a controversial point and will generate discussion, but that I think would be a healthy discussion for us to talk about it. I think there was not sufficient discussion about this property over the last 10 years of this question. Nevertheless, halos, we now see that halos do have physical boundary that can be argued as a physical edge of the halo. Whether this mass provides us a lot of advantage in modeling different properties, I think remains to be seen because it's relatively unexplored. For example, we don't know exactly what will be the mass function of halos if we define masses within the splashback radius. It's definitely useful, at least in some aspects, it's clear already. For example, the aspects of understanding assembly bias and what quenches the galaxies and out to what radius the galaxies are quenched. Stay tuned for the next talk where you'll see, and also this is related to assembly bias most likely, because it does, splashback can be shown to be contributing, the halos within the splashback areas are contributing to assembly bias. And stay tuned for Surhood's talk next that will talk about it. And I'll give you an example that concentrations depend not only on halo mass, but also on secondary parameters. And just one example I think, of generic trend that halo properties will depend not just on mass, but on other properties as well, as will most likely galaxies, but modular the fact that some correlations that we see in halos loud and clear can be decorrelated by the process of galaxy formation. But we don't know the degree of this decorrelation yet, so this is something we have to keep an open eye for. Thank you.